So I'd like to begin, actually, with the binary phase diagram, and I'd like to talk about reading this binary phase diagram. Not so much the numerics, but I want to point out that when you get to these more complicated diagrams, it's necessary to think about, well, it's not necessary, but it's helpful to think about the phase fields present. And there's other tips and tricks here I'd like to show you as well. So this is a phase diagram for aluminum nickel, and the x-axis or the y-axis is temperature in degrees Celsius. An important point here is that this is in atomic percent. This diagram also gives weight percent, but the important thing is to make sure that anytime you start working with the phase diagram, you know if you're looking at atomic percent or weight percent. It makes a big difference. The two and the way you read it is equivalent, but it does, well, you get things completely wrong if you read them wrong. I mean, if you look at this weight percent, I mean, this is very much a nonlinear scale associated with the ratio of weights of aluminum to nickel. So in this diagram, it came with labels, and I erased those. And what I wanted to point out right here is that you don't necessarily need those labels to know what's going on. You just need to think about the ordering of phases. So I'm going to zoom out a little bit here. So we're going to put the labels in the diagram. Let's pick a color. So of course we know up here this is liquid. And now we have the rest of this. If we look at it, it's not entirely clear, at least without starting to write things down, what phase is two phase, what phase is one phase. So what you can do is you can look at the bottom, and you can start by looking for regions for line compounds. And what you have here is you have this point is a line compound. And you know it's a line compound because it comes up and it intersects like this, making a T. Well, that's not really a T. That is actually something that looks like this. Right? But you know that this is a single, either a single compound or a single phase, because it's going to have this shape, and at this point, you're going to have three phases. So you're going to have, and then you also know that this region is going to be something and liquid, right? Because it borders with liquid. So that tells you that this region has two phases. So it's going to be, say, liquid plus, I don't know, alpha. And then that means that this region has to be a single phase, say like beta. So that way you can have no more than three phases at that point. So at this point, here we have no more than three phases. And that's necessary by Gibbs phase rule. So that tells you that this is a line compound. And if you look at it, it is 25%. So that tells you this line compound is going to be Al3Ni, a 3-to-1 ratio of aluminum and nickel. And now that we've identified a one-phase region or a line compound, then we know that on either side of it, it has to be a two-phase compound, right? So this has to be Al3Ni plus something. This has to be Al3Ni plus something. Now that something is aluminum, and this aluminum here is being treated as a line compound. Al this region now is a single phase region, and we can call this, say, gamma, or whatever phase we want to call it. We can tell it has solubility because it has width, so it's not necessarily an elemental. But we know that, so I'm going to call it gamma. But based on the compositional range, and based on what we know, and well, you don't have a list, but if you had a list of compounds, crystal structures, you would know that there's a crystal structure which is Al3Ni2 that is in that range. So this is going to be Al3Ni2, which then makes this region two-phase, and makes this region, again, one-phase. And this one-phase region, look at that, it's right here at 50-50. So this region is Al(Ni). And this Al(Ni) goes up, and you've got congruent melting as it crosses up into liquid. And if you want to think about it, that also you can think of as a place where you could draw a I can't draw it there really, but draw another line and have this be a series of paratectic diagrams. Same thing as, say, here. Or maybe it's better to draw it this way. Like that. So now we've got this. Which means that single phase, that means that this now region we know is Al3Ni2 plus Al(Ni). Makes this two-phase, makes this single phase, and that single phase region is Al3Ni5, and again, you really need to know the crystal structures for that. Make that two-phase, single phase, that single phase region here is Al(Ni3), right? It's at 75%, which makes that two-phase and makes this single phase, and single phase with a fairly generous solubility. That is Ni. So it's Ni, which can have aluminum soluble in it. So then I'm going to change the colors here for the sake of being able to see better. That means that these two-phase regions, this region is Al(Ni) plus Al3Ni5. That makes this two-phase region Al(Ni3) plus Ni. So we've labeled all of the phases that are in our low temperature limit. And that means that now we can go and we can label the phases that are above them. So we know then that this region, that little tiny triangle here, is Al plus liquid. This region On one side it has the line compound, other side it has liquid, which makes this Al3Ni plus liquid. This region, one side it's got single phase, our Al3Ni2, other side we've got a liquid, which means this is now Al3Ni2 plus liquid. This region has AlNi and liquid on either side, which means it must be AlNi plus liquid. Same with that. That region is AlNi plus liquid. This region, a little slice, that is nickel and liquid, Ni plus liquid. And that leaves this region, and that region has on either side of it AlNi and AlNi3. So this is AlNi plus AlNi3. So we've gone through and we've identified, zoom out, all of the phases that are present here. And this was just by process of elimination and knowing the Gibbs phase rule. So the Gibbs phase rule gave us that we had a line compound. Again, when you have regions like this, if you don't know the composition exactly, it's a soluble compound. We give it some Greek letter that represents a particular compound or crystal class. So this is labeling a complex binary phase diagram.